All right, welcome everybody to today's life science session. Today we are going to be exploring some more quantum, and specifically we're going to probably, hopefully look at the directions of inference, uncertainty, and Hopf fibration, but we are uncertain about those specific state spaces. So we'll just have a quantum agenda for today, and sort of hopefully cover the state space of that of those topics.
Yeah, I don't know where it goes. I just have some rough sketch right now what I'm gonna talk about. It's mostly about just like an overview, or maybe just like up-to-date information about what I've been doing and what I've been researching and looking into. So yeah, but it's again, it like involves a bunch of quantum foundational stuff and how you can apply our framework to it and do some nice quantum geometry and how you relate it to the probability theory. It's like all the same topics, maybe from some slightly different direction now, but just to set it up, it's like again we're thinking about quantum states as distributions, right? But we want to think of them as not just arbitrary distributions. They're distributions with some lower bound on uncertainty, right? So or entropy. You can think of it it's like in two ways. You have you have probability distributions when they can even generalize definite states. Like you can have definite value, like a coin always lands on heads, something like that. It's completely deterministic. So in probability theory, those things are out, and those states represent minimum uncertainty, right? But now you can think of quantum states as some kind of distributions, but have some lower bound on that uncertainty. And geometrically, those uncertainty are usually represented as, I guess I'm gonna like also, yeah. Let me just show this kind of pictures. I have a nice pictures for entropy, which is one quantifier for uncertainty when in different dimensions that you can actually visualize, right? This is this is our probability simplex for a single coin, which is just a single line with a single parameter. But if you compute a Shannon entropy for each of those point and colorize it, there's some kind of quantity you can assign to each of those distributions on each of those on each line. So you can colorize it by the entropy. So it's like you can see that the lowest entropy or the maximum information, I guess, is on the boundary of that simplex, is in that definite states where the coin is always lands heads or tails, right? And in the middle is a state with the maximal entropy, 1 in this case. It's like 1 bit of entropy, so it's the most uncertain state.
So so what's the definition of Shannon entropy, just quickly, so that we can build an intuition of what makes it more or less entropy?
Well, the Shannon entropy is simply it's like a sum. Let me it's like a sum, right? Minus p log p, something like that. Write it like this. Maybe it's log 2 usually.
P being the probability.
Yeah. In this case, p is just in binary case, it would be if you're given the probability distribution p 1 minus p because it's normalized, right? Here it's usually like you sum over this thing, right? So in this case, it would be minus p log p minus 1 minus p log 1 minus p, something like that, right? So you can at each point you can compute it. For example, let's compute it at just like given this vector, you can also do it like this. Let's write an actual function, why not? Right, so it's p log 2 of p, and if p is a vector, we just total it. Of course, there's some. I think I have this variable already. Right, of course, if it's like 0, there's going to be some problems. But if you just feed it one vector like this, you can get this value, right? And if you plot it from p from 0 to 1, you get some curve like this, right? So you can see the same curve as here. That's why I'm putting it kind of like a pouch on top of the simplex, which is like, I think it's a nice visualization, right? So this is like the highest entropy. Here's at the lowest.
Is there something to say about like how compressible the state is. In other words, if it's one coin, just with heads every single time, that's a very low, or it's maximum information, but it's kind of like you could just summarize it very easily. Whereas if it could be two different states, 50-50, it requires more space to represent that mixed state.
I think
something
you,
like
you
that.
don't
Well,
have
it's
to
like
over.
I guess you could think of it like surprisal. Basically, if you have a fair coin toss and it's heads and tails and it's dispersed as a history, where heads and tails are peppered in with equal like ratio, then you have like a maximum. You don't know what's going to happen next.
Okay,
But if it's
okay, that makes sense.
if it's mostly heads and it's only like 1% tails the whole time, then you're usually never surprised.
Yeah.
So you have a low entropy on that probability distribution of 90-10.
Yeah, you can define this surprisal function, which is kind of inversely proportional to the probability. So it's the more probable, the more probability is away from average 50-50, the
Less surprising.
yeah, kind of.
So
But
what
also
if,
some.
what if you had like a fifth and a fifth and then like 3/5?
It's just on the coin. It's
One fourth if you can get this one. It's like, right? So it's somewhere here. I guess. This is 1/5. Can I do it like this? Oh, I missed it. It says I don't know what's going on here. I'm not messing anything up. Why do I 2 points? Oh, maybe it just needs one more wrapper. Okay, that is. Maybe put it afterwards. Otherwise, it's like there. This is particular one for 1/5 for 1/5.
Yeah, so you go to 0.2 on the x-axis, and you see where the line hits there. My question was about the connection to compression. So it seems like there's something about like the more compressible the state, the less the entropy, something like that. That seems to be linked to information and surprising. Like the less surprising things that could emerge, the more you can the more you can compress something. So for example, if something happens 90% of the time, if it's heads 90% of the time, you could summarize that pretty much by saying it's almost always heads, and you'd be correct. Whereas if it was always 50-50, you wouldn't be able to summarize that. You'd have to say, I don't know.
If you saw a string where it's mostly heads, you can compress. You can do run length and encoding on that and compress it pretty heavily.
And you'd be pretty correct. You'd be relatively accurate.
Yeah. So of course you can reverse it. I don't know, maybe information sometimes it's more easier to comprehend, right? Instead of talking about entropy, which is you have to always mentally connect to some kind of compression, surprise, or whatever. So like the negative entropy, neg entropy, or information, which is usually just you can just define as maximum entropy minus the entropy, right? So that's how we can define the entropy. This is because this is just a list. Then in terms of bits, I guess that's
you mean information. You said you meant to define information.
Yeah, to define information. You can define it like something like this, right? When the length of the vector is 2, then it's like 1 is the maximum number of entropy is going to be 1 bit, and then you just subtract the actual entropy, and that's how you can define the information. So the definite deterministic states has the maximum information. They have 1 bit of information, right? And the random state, 50-50 state, has the 0 amount of information. So you can't really, and I guess you have to have like in the maximum, the lowest rate of compression, right? You have. So that's more natural to think about information. And we actually come back to information later. essentially there's like more pictures. This is like this is full one. Essentially do it for 2D, but now the same kind of pouch around the simplex looks like some kind of parachute or whatever, right? But it's the same idea that you also have a simplex in 2D, and at each point you have an entropy, right? In 3D, now we actually, when we go to the where the quantum state and quantum case emerges, because now you have a block sphere embedded in that simplex, right? And that's naturally bounds your entropy and your uncertainty. So any quantum state which lies inside of this block ball have this lower bound on uncertainty, because the lowest uncertainty lives in the vertices of that simplex probability. So this is a definite state. This is not totally definite, but it still kind of have a very large information. So naturally, you can think of any quantum states. It's not a generalization of probability theory in any way, like people start like to think about quantum theory as some kind of requiring some additional laws that you have to do, add to your probability theory, some kind of new measure. In this case, quantum states themselves is just a special case. You just constrain your probability space to some states that has some bound on uncertainty. So you can think of it this way. So on block spheres now, this represent those bounds, right? And more concretely, again, it's like some tetrahedrons labeled, right? Given a quantum state, you can now you can pick some nice orientation of those tetrahedron, though, so that you can label each of the vertices in some natural way, right? This is like our common quantum state is just a definite zero state in quantum computation, or maybe it's an up state representing spin. But in some particular basis, like maybe given this tetrahedron over here, you can label these vertices. It's kind of being in between those three opposite sides of three axes or whatever. You can just stare at it and you see that why you should label this state like with three different points on those axes, right? Because it's like points directly in between them, right? And you have three of those that are natural duals. So this is like a cool picture, but now we want what we want to do with it, right? So this kind of choice of orientation. So just a reminder. So we are basically mapping any quantum state to a probability vector, right? But this mapping requires, first of all, you have to wrap your quantum states, your block sphere, with the tetrahedron, which is a probability space. But the choice of orientation is quite arbitrary, right? So there's like this is a very nice orientation because it labels all the quantum states with some particular meaning, but the orientation itself is quite arbitrary, right? So what we want to do is okay, we don't want to choose a particular orientation. We want to represent, well, first of all, what we want to do is the goal here is that, okay, quantum states are probability distributions, but how they are realized in nature, right? What is the realization of that probability distribution? There's no way that the actual the nature actually encodes the probability numbers as a vector, right? It's kind of hard to imagine. It's has to be some particular, like in the analogy here, maybe with the statistical mechanics and all of that. You also deal with the probability distributions there, but you have them strictly because you have some finite large number of molecules, like in a gas chamber, you have some Avogadro number of molecules, and that's why you have the statistical ensemble. Here you have a statistical ensemble for another distribution with a finite dimensional, but you have to realize it somehow with some kind of ensemble. So you have to actually sample some points, right? Maybe finite set of those, maybe of the same kind of order as Avogadro number, but it doesn't matter. Some statistically significant number of them. And for each of those orientations of tetrahedron, you essentially can sample a point, right? You sample one of those vertices, right? You pick an orientation of a tetrahedron that you wrap your quantum states with, and then you sample one of the points from that distribution that it gives you, right? And that's essentially, you can like put all of those, essentially you can simply, without thinking how you do it like more cleverly, just pick three angles. Those are usually what allows you to pick an orientation in 3D space, right? The so-called Euler angles. You kind of roll, pitch, and yaw angles that allows to orient a plane in this kind. The same way you have to pick 3 angles to orient tetrahedron in 3D space. Right, for all of those orientations, you can sample them uniformly or with some more clever distributions. You can just pick a point here, and that represents a tetrahedron. You can compute the probability vector and sample from it, right? You can label them somehow, it doesn't matter. There's 4 colors, right? So that's basically this ensemble in this all possible orientations, or some finite set of those. You can represent a quantum state as a particular concrete ensemble and not just a probability vector. So from this statistical set of points, this cloud of points, you can reconstruct the quantum state. All right. So those are kind of equivalent representations for qubit. But again, all right. But this kind of picture may be not very natural because what we usually do with the qubits and quantum states later is some kind of rotation again, like maybe applying some unitary gate, which is a double cover for rotation, but don't worry about it. It's like we're usually rotating qubits around in 3D space if we're just applying some quantum processes to single qubit. If it's a unitary revolution, unitary operator is just rotation. So essentially we just
Can you go over this plot again with the colors? So I understand that this is setting up or layering in angles to have a orientation of space. And once the tetrahedron is oriented in this probability space, you can sample. What are you sampling? A quantum distribution?
Yes, it's like more concretely you can say, like pick a random state, right? Quantum state. It's some, what the hell is it thinking? Okay, it's like pick a random state. This is just conventional quantum amplitudes for your 0 and 1, right? When you pick an orientation, it's like it's essentially equivalent to transforming it to some space. This is one of the favorite ones. This is corresponds to this tetrahedron, or maybe another one. One of those, right? It corresponds to one of those tetrahedrons. When you transform your quantum state to this phase space representation, its amplitudes now just a probability vector, right? We call it capital P. So this is a probability vector. It's all like positive numbers. If you sum them, you get 1, right? That's a definition of a probability vector. That's the probability vector that we sample from. If you choose another one, like maybe I already have called here, right? Here actually how I do it. It's like that's how you can sample uniformly, more or less from all possible orientations, right? And then you can compute the earlier angles from that. So essentially, this is like sample all earlier angles uniformly across all space of orientations, more or less, right? And then you can just, for all of those 10,000 of those, compute basis elements, right? And then you can transform a random state to each of those bases. So there's like essentially there's like 10,000 probability vectors. Like, for example, like this one is a probability vector. This one is another probability vector, right? And you can sample from each of those, and those represent like some color, right? One of 4 colors. That's how you build this picture. You sample from each of those probability vectors, and then you just map them out in this simple early box, because you can just have 3 angles that you can just represent on all the 3D axis, right? So that's how you can visualize simply. This is like the simplest visualization for the space of rotations and how you can map your quantum state into it with some colors.
Yeah. Is there a pattern to the colors, the way it plots out?
Well,
or
if
is it
you
uniform distribution almost?
well, it's not. It should be a pattern. It's just maybe hard to spot it. It should be. It should concentrate. There's some clusters, definitely, because it's like maybe in some because some orientations maybe have a tetrahedron pointing to the north pole, right? And maybe if you're sampling, it's like maybe let's try to figure it out. It's like if you take 0, that's the block vector that's just pointing to the north pole, right? If you sample all of those points here, see what maybe clusters are more visible or something. I don't know. It's kind of, this is like has more blue in it, right?
Can you zoom in on that block a little bit more so we can see those pixels like zoomed in? Okay. So you can't turn those colors on and off easily just from the plot there.
I guess I can. Just let's see. We just do if greater than 2, make it white. Something like that. But for now.
White will can you make it invisible or transparent? Because white will block out some.
No, I don't think so.
Okay, there we go.
This is just one of those. That's kind of pointing into one direction. Right, maybe.
Spin it up a little bit, like lay it flat. Yeah, there. See how it's like divergent in
Yeah.
the middle? Looks like
Yep. So it's kind of centered around some angle. So what would you expect? It's like you pick some orientation in the block sphere, and the actual orientations that align with it would have more probability of actually sampling that point.
Yeah.
And yep. But then I was thinking maybe, of course, it's not a very natural way of sampling angles, because probably when you try to orient it, your actual points would orient to points that do not longer exist in this particular ensemble. That's what you usually get. For example, you sample this random set of orientations, but when you apply some quantum gate which reorients all your given tetrahedrons, right? And when they orient them by your given rotation, they not necessarily map to some orientation that's already there. So you can just swap around points. But you want this operation of rotation, of applying unitary transformation to a qubit, to be a permutation, because you want to preserve information. Because the permutation is actually a deterministic operation. It doesn't like reduce it to noise. So you can permute indefinitely your set of points without losing any information. And that's what actually how we think about unitary transformations. But those transformations preserve information, right?
Yeah.
So we want some proper set of points that actually are closed under all unitary transformation. But we also want, maybe not, let's not go to the closed yet, but next we're gonna go to some how we can sample what actual space of all orientation is, right? The most famous visualization and representation of space of all orientations in 3D is the Hopf fibration. Hopf fibration is essentially how you can visualize the space of all the possible orientations of a tetrahedron, right? Usually it's like represented using stereographic projection, right? It's like essentially you given 3 early angles and you do some crazy thing with it, map it to the point on in 3D space. It's like pick 2 early angles, give you like a longitude and latitude. So basically point on a sphere, and the third angle is like a circle emanating from it. That's the fiber. That's why it's called a Hopf fibration. So that's how you can represent any angle. And the interesting thing about it that those circles don't even intersect, right? So they kind of map and span the whole 3D space, and for each point you can pick the represents just a single set of angles. So that's like a classical representations. But you can also, I was playing around with it because those circles in the stereographic projection, they actually some of them go to infinity, right? But maybe I want to constrain my visualization a little bit. So I also try the Poincare projection. Now all of those circles actually are now bounded to a sphere. Right now you essentially can pick a point inside of the ball, and you can find a circle there that parameterizes your orientation. So now you have a representation for all possible orientations of tetrahedron just mapped to a point in the ball. Something like that. And that's how it looks like. It's kind of funny pictures. But the more interesting pictures are, I think, are here. When I've tried, well, maybe it's like no news to somebody, but I have first time missing like this kind of surfaces. This is essentially just pick one of the angles from those 3 and try to turn every other 2 angles to a surface, and then just rotate one of the angles, right? It's like one of the angles is just like essentially, that's how we can span the whole any point in the ball, right? It's like,
okay.
right, you can do it in 3 different ways. This is the most boring one, right? But if you those two represent some nice rotation surfaces. So like you can, it like looks weird. It seems like the surface is changing, but actually just rotating, I think. So it's
No ways. That thing is definitely doing weird stuff in there. That can't just be a rotation.
but I think yeah, maybe it's moving a little bit. Yes, but actually it's very hard to tell.
It's rotating and moving.
Yeah.
I'm sure. Yeah.
So each point of
But-
these
but this
balls
one-
here,
this one-
inside the sphere, correspond to a particular rotation frame of 3 dimensions, right? And
So
these
weird.
surfaces are like foliations in the space of rotations.
Yeah. It's like just for
Yeah,
one given angle,
It's doing this.
you plot all possible. You plot a surface for other 2 angles in this Poincare projection. So, and the reverse of that was like given, yeah, it's funny. I don't know. Seems bizarre. Yeah, it's doing something, not just rotating. This one is definitely rotating.
So is it supposed to cover every possible point within the ball? Is it supposed to like?
Yeah, I think so. It should be.
So does that do a full 360? Does it rotate twice? The one on the right.
Well, kind of is because here it rotates once, but
Yeah, it has
does
to rotate twice.
because
So
the angle is actually it's very large. So look, I'm going from 0 to 4 pi. So it's actually 2 rotations.
yeah.
If you count the angle.
Oh, I
Yeah.
see. It's rotating over a horizontal axis. Or maybe you turned the plot.
Maybe
It's rotated and then also like
yeah. Anyway, maybe it's
moving.
like one of those belt tricks, but maybe it's not the best visualization for that.
Oh, keep turning it
There are
so
much
that we
better-
look down the other axis. Like turn it up a little bit. No, the other one. There, that one.
That's not going to show you anything.
Yeah.
We can see that there's a spin to it.
Oh yeah, there. That's obvious because how did it go from there to separating out? Yeah, see, it's like moving up and down as well. It's crazy.
Yeah. So that's just fun. Well, that's just a simple thing I've looked into how to essentially also another way of thinking of those, picking the orientations for representing our qubit ensembles, right? Just instead of sampling random angles, you can try to think how to parameterize, or you just randomly pick a point in the ball instead, and using
So
this projection and map it to an angle.
So I've got a question then. How does this relate? How do these 3 separate manipulations relate back to the Hopf fibration? Is it just like splitting the Hopf fibration up into 3 separate things?
Well, it's kind of, well, this is the Poincare projections of all those circles, right? This is how it's usually represented, maybe with more colors, right?
Yeah,
But
yeah.
you can project, this is a stereographic projection, but you can map it to a ball, and then instead of just showing a circle, you can add one more angle and show a surface and rotate the third one. And that's how that's how those surfaces are mapped.
Okay, so it's the exact same thing, it's just projected in a different way.
Yeah, just select a special set of circles in a way, or for all the angles between, like maybe between taking theta from 0 to pi.
Okay.
Something like that. Right.
So the Hopf fibration always has 3 things to it, 3 like kind of segments in this. Even in the stereographic case, you have like let's call it like layers.
Yeah, well, yeah. It depends how you also parameterize it, because it's like you can draw the circles continuously, but you have to pick the angles for other ones to pick your circles, some discrete set of angles at least. It's like this is like a just clearly I'm just picking some discrete layers for those, but they're also going continuously, like here, right? We can pick the cylinder or any cylinder, basically.
Okay, let's see. Interesting. And what you were saying earlier is like every single one of those lines is basically a full circle. It's like it's its own circle.
Yeah. Let me play as one of the viewers correctly mentioned that we should just visualize it. What's kind of becomes laggy a bit. Just at least visualize one of them. The most pretty one. Okay. Okay, but the motivation is not doesn't end here. Like the next question I just ask, okay, we just can just map again the same kind of problem that it's not if you just sample points randomly, you still have this closed problem that if you try to orient all the points, they don't correspond to permutation necessarily. So you have to pick your points wisely. And the mathematically correct way of doing it is actually picking a finite subgroup of all the orientations. And by the way, orientations also correspond to quaternions. So now we're going to do some quaternion math. And turns out there's a maximum largest finite subgroup of quaternions that you can have. And it's not very big. I was kind of surprised. I didn't know that. It's like it's just essentially like this graph, which is called 600 cell, which with 120 vertices. So essentially just 120 elements and 120 orientations that if you orient one orientation with another orientation, you get another orientation from that set. So it's closed. And that forms a group, a subgroup of quaternions, right? So we have a graph, but there wasn't any way to actually have.
And this is the largest finite multiplicatively closed set.
Yeah, group
quaternions.
Yeah, I think it's the largest.
Mm-hmm.
Maybe someone can correct me, but maybe it's at least either it's known or it's probably largest. I think it's probably largest, but I may be wrong. I think it's proved, right? And so if you, this is like a little bit what I've done, and essentially, if you pick all of those 120 orientations, that's the set of tetrahedron, just overlaid over each other, corresponding to those all of those orientations. So that's a nice set which is closed that you can pick and sample from just those to represent all the ensemble of your qubits, right?
Looks
and if
like
you,
a spiky.
yeah, that's also nice. It's actually because it's a icosahedron, right? And that's what actually it is. So that's a
Icosahedron.
oh, or maybe it's not one. Was it? I think this kind of graph somehow relates.
It has
to
the same type of symmetry.
Yeah, it's at the same time of symmetry. Essentially, all the ways to orient icosahedron is essentially this symmetry, finite group orientation. So it's finite. It's not quantumly universal. So you can't really represent all the possible unitary gates for a qubit, but it represents a nice finite set, right? And maybe, well, maybe just and it's I was kind of surprised that it's the largest finite set, but because I really want an actual closed thing with more elements in it, so that at least you can approximate. So this is like a nice fundamental question here, is to ask why is it ends there, and if the actual world is discrete, right? And we can't really orient completely arbitrary our like spins of the electron and all that. If it's actually discrete, why would it be not closed, right? Because it actually can be arbitrarily oriented. Does it mean that it means it only approximates like a mapping some orientation to the other orientation maybe twice. So it's not like some bijectional that there's some problems of being closed under rotations if you make it finite. And that's kind of weird. I don't know what to think about that, but that's what I learned.
Oh, I see there's a cube in there. Or are these all cubes? Oh, maybe,
those are
no,
all
I was wrong.
heterohedron.
I was wrong.
No, there's
all
no
just
90-degree
tetrahedron.
angles on that. Yeah.
Yeah.
So can you just explain what you mean by finite, or like the
By finite,
Hammock?
you simply like the Hopf fibration and the set of all possible orientations are clearly infinite, right? There's like a finite continuous space that you can orient all your tetrahedrons with. But if you want, but you can, the point that it forms a group because you can orient a tetrahedron with another tetrahedron, so to speak. You can multiply them together, right? That's what you essentially do when you do some quantum computation on qubits. So the search for finite ones is just a question: what if the space of all those possible orientations has to be finite? Because we want to represent. I think the motivation here that we want an ensemble, this probabilistic ensemble of points, but we want those points to form some finite set, and so that you can still make sense to just orient all those points and keep, which would just correspond to permutation of those points.
So what is
Right.
a finite set? Maybe I should ask that.
Just a finite number of tetrahedrons are here. It's like 120 things. It's a finite set,
Okay.
right?
Well, yeah.
All those tetrahedrons are here in this picture.
So
Maybe you can-
I'm missing all the steps, maybe level. So how are you deciding how many tetrahedrons to put into this finite set? Is it an arbitrary number?
But I'm not deciding it. It's like here's I have 120 of those, but it's like constrained by the fact that all possible there is no finite subset larger than this that keeps you close. It's like if I add some other tetrahedron to that set, right? Maybe I orient it slightly off, right? If I then orient all my 120 orientations using that tetrahedron, it's going to generate even more tetrahedrons, right? That are not in that set. And if I multiply those tetrahedrons with those, it's going to generate more and more. It essentially makes an infinite group. It's no longer finite, right? And that would essentially make our quantum computation set of gates of these rotations universal. So this set is not universal, but it's like large enough that you can still approximate a quantum state even by a single sample from each with some real accuracy.
So we're saying this is the only such finite set that exists?
It's the largest one. They're the small ones. They I think they correspond to all those platonic solids and their symmetries.
Interesting. Wow.
So just there's some good geometry in there, which I don't know, not familiar very much, but I think it's quite nice.
Very cool.
But okay.
Right. Yeah. No, it's an interesting story. So we used 3 Eulerian angles to parameterize the space of rotations. 3-dimensional frames that you can have.
Yep.
And you can also use the 3-sphere as a manifold, so the hypersphere. So in 4 dimensions, I have this ball of radius 1, and the 3-dimensional volume, the 3-dimensional surface area of that thing is like a space.
Of orientation.
The 3-dimensional manifold, and each one of those points corresponds uniquely, right? Or is it a double cover to rotations?
I think it's double cover, but we are dealing with quantum computation, so it's actually we need a double cover. So that's why double cover is essentially why we have 2 tetrahedrons here. I think. I don't realize. I don't think it's not a concrete proof, but I think it's my intuition tells me that because orientations is just how you can orient one tetrahedron, but because you can have duals to each of those, those will essentially represent reflection, and that's how the double cover arises. Essentially, quantum computation is not just arranging; it also can reflect your tetrahedron and make duals of those. So it's a little bit like twice the space of all rotations. All right, that's a geometric story, but now we want to make an inference story and how it relates to like things like because again we made this nice connection of geometry of space of rotations and probability vectors and how you can sample it and represent qubit ensembles, right? But now so you can conceivably imagine that all the quantum states can be represented as just statistical ensembles. So what's the big problem there, right? Why can't we actually do it? And the problem lies in how those probabilities and those ensembles are processed, right? How we act on them and how we measure them. And here I'm gonna like show you how we can think of those processes in the case of measurement as a sort of inference, right? So essentially, the problem is that again, because we are doing some fundamentally, our information has to be conserved, right? This is just keep in mind this fact, right? So it's forbidden to destroy any information, and also increase it. So in a way, that's what it means, even when you do the measurement. And here how you can think about this fact, what it actually means to make a measurement. It's like this is like a diagram of the measurement of the quantum state. It's like what is hidden between this double line there? What is actually happening when you perform a measurement? But why is it happen so that we preserve the information, and how is it conserved? There's like one way of representing it as essentially you have a measurement device, right? So you have a quantum state that you're trying to measure. Maybe it's a electron, maybe it's a photon, maybe it's just a qubit in your quantum computer. You're trying to couple it to some device. That's how you can essentially represent the measurement. There's some particular entanglement of your device with your quantum state. Your device is
I think Nick's frozen there, but
I blame the servers.
we have a quantum servers, then we wouldn't have to experience the analog lag.
this,
on
but all
on
the
different
information
episodes.
about it's
Wait,
like it truly breaks out.
pause. We had a intermission there with some interference from the network.
Am I
So
back?
we missed. Yeah, you're back now.
You cut out for a minute.
Yeah.
Sorry.
Before we rewind, can you zoom in maybe to 150 or something just to get that to larger
Oh, you did, yeah.
zoom in? That's great. Okay, so I think the last thing you were saying was, oh shit, I meant whoops. I don't know what Dugan, what is he saying?
You're
Oh,
taking
don't sweat.
measurements with these qubits.
Yeah. So I'm trying to explain how the measurement happens. First diagrammatically, and then how the information transfers. So so we can see the actual transfer information, and then try to explain it in terms of probabilities and all that, with all the above. All right. Here, I was trying to explain what is behind these two lines representing measurement, and that you can represent it as there's some kind of measurement device which corresponds to a completely uniform mixture macroscopic device, which is like acts like noise, and then you entangle your particle or qubit to it, and then you trace out the device. Essentially, you read out its pointer variables, whatever the reading was, and then you trace out in a way you more marginalize the probability distribution. You can also think it like this way. Like here, in terms of probabilities, what this means, right? We know that we can transform or think at least of our quantum state as just a probability distribution with some particular orientation of a tetrahedron, or maybe in multiple orientations, right? Then what the measurement like this particular construction means. It's like here just I'm turning it into a matrix, and it's nothing else that just some kind of mixing of some of the states. So it's just some particular conditional probability table. If your particle is in first state, you just turn it into a mixture of first and second. And it's the same for the second one. So it's just some completely mixing of that particular distribution. But when you do this, like this happens, this particular map and this particular trace thing. Let me actually show what trace looks like in this representation. I think that's important because it corresponds to marginalizing your distributions. So if you in this basis look at the actual state, it looks like do the table there. Essentially like looks like a sum. So given a state, you just sum over them. That's equivalent to just summing over a probability distribution. It means that if you have a how we can do it, like if you throw away, this is like me live coding at this point now. Okay, so if you just do not trace our device, we don't read it out yet, and just measure the quantum state here. This would represent a mixed state. You can also do the same kind of thing with the mixed state. And this mixed state would be just some particular probability distribution. But now it's a probability distribution over both device and the qubit. Right? This is like this is the device. The first state is device. The second one is the qubit. Right? So it's a probability distribution. I think it's if you can make a tensor out of it, right? So that the first the rows now is the device, so we can just completely sum over it. That's like computing a marginal, and you get the same result as just measuring. I guess if you just apply this matrix to distribution P, I think so, right? You get the same result. So we just interpreting what the hell diagrammatically it means to couple to a device and then trace it out the result. It's just marginalizing the device, just summing it over. But what it actually does, this operation is not very physical, right? Because when you're marginalizing and throwing away the information, well, you're throwing away the information, you're destroying it, right? Maybe let's just see that why it's destroying it. We started with the state row, which has one nominal entropy equals to 0, which means it has information or purity. I guess you can also quantify information as purity as information, right? It's one bit of information. So we had one bit of information corresponding to a quantum state, and you had 0 information in device because you consider it's kind of noisy, it doesn't have any information yet. You couple, as soon as you apply, when you apply this thing, essentially execute this circuit, right? This circuit. When you couple your qubit to an environment, it will make a mixed state with one bit of entropy, but now maximum entropy is 2 because it's 2 qubits, right? We now have a device and the qubit, the original qubit, the maximum in entropy is 2, so it means we still have the same number of information in there, right? We still have one bit of information after we coupled our qubit to this noisy device, right? So that's so far so good. No information was destroyed or created, but when we do this tracing operation, marginalizing over the device, that's where the information is get destroyed. So in that sense, this particular operation is not physical, right? You have to explain where the information is going or how to compensate for that. And how we're going to compensate for that, it's really clear. This is like all about like geometrically, it's all about like expansion and shrinking. I don't know what's the proper way of what the proper terminology for those, but those essentially corresponding to if you think of quantum states as just vectors in this 3D space, if it's just a single qubit, right? Some block vector, which is also inside of that probability simplex, you can either shrink it or like extend it. Maybe it should be called extension. I don't know. Right. that's how you can see the change in information really clearly. The closer your vector to the center of the block sphere, the less information it has. The farther away it's from the center, where's that picture I had at the beginning? Here, it's like in the center, it has the maximum entropy, 0 information, right? We have a quantum states. The pure quantum states have largest amount of information of 1 bit, right? So the constraint and uncertainty, they can be. It's the von Neumann entropy is 1 bit, but if you recompute it using the simplex, which is a 4-dimensional thing, it has to have like 2 bits maximum of Shannon entropy, but it never reaches that. So that's why you can say that there's some lower bound on uncertainty or maximum bound on information, I guess, right? So this idea of shrinking and extending your probability distribution just means you can just extending your vector if it actually got shrunk or something like that, right? Because when you, for example, do this discarding of your device or tracing it out, it shrinks your probability or your block vector. It makes it mixed. That's what usually, when you think about the projection, you mix your quantum state, your qubit, so that now it has less information than it was before. Okay? So in order to compensate for that loss of information, you have to somehow inject that information back, right? And this injection is exactly just an expansion along the direction that your vector is already pointing, right? You're not actually rotating anymore. You're just either extending or shrinking the same vector. So that's how we can computationally compensate for that. So essentially, what that's what you, in combination with this destruction of information by marginalizing your device, you can call all this operation as inference in a way. Just to clarify it, concretifying this term in a way, right? This is the thing that allows you to this particular expansion of the qubit, like extending it across the direction that it's already pointing and injecting information back that it's lost due to discarding of the device. That together recovers the probability distribution that we are essentially observe in experiments, right? Without this expansion, you have some larger uncertainty that has to be. It's like less information in the distribution than it has to be because this on itself is not physical, this operation has to be included there. But the problem, yeah, okay.
That's why the universe seems to observers like it's expanding. No, I'm joking. That's my own take.
Yeah, it's not really that. You can you can think of this expansion. This is literally like this is the shrinking map, right? Expansion is just the inverse of shrinking. So if this is the shrinking, but you can think of shrinking as essentially this is you can call this some kind of factor, shrinking factor, whatever. It's like a convex map, probability map, stochastic map. It's like with this probability, do nothing, right? Or inject noise. This is like just a constant matrix with like a uniform distribution. So that's how you can think of shrinking map. It's like with some probability you're injecting noise, right? It's just you're given some sample, you throw a coin, and given if it's wanting heads, you do nothing. You just take the same sample back forward, move the same sample forward. If it's heads, you just produce some random results instead, right? Something like that. You're just injecting noise, and this is like a quantifying. This shrinking factor quantifies the noise. So it's clear how you can, and this process is simple. It's easy. It's like you can physically imagine it, right? That's how I just described how you can shrink and get rid of information. But injecting information back is a completely that's completely unintuitive thing. How you can, especially on the level of samples, it's clear that you can multiply a probability vector by the inverse matrix. That's fine, right? But right, because it's just the inverse of the shrinking matrix. It's like for this one is here, this one is here, whatever. But how you what does it mean to actually do the expansion? It's not clear because the actual numbers here, and that's where the negative probabilities come again, right? Because even though the shrinking map looks exactly as a conditional probability table, right? It's just some conditional probability or stochastic map. When you sum up the columns, you get all the ones and all the numbers here between 0 and 1, right? So it's a normal stochastic map that you can imagine doing in a classical world, just on a level of samples. But this inverse thing you can't really imagine, right? Even though, but you can, but that's what it requires. That's what's required for quantum computation to make sense, and to produce the actual results that we see in the lab.
Yeah, well, it kind of does make sense if you think about, multi-way systems and observers and like which way path information and that kind of stuff, like in a fuzzy way, I guess.
Yeah, fuzzy way.
Yeah.
But here we just you don't have to think of like, you can reduce all the weirdness in a way into just this single expansion map.
Yeah, which is pretty cool.
It's like for every arbitrary, more concretely, it's like for arbitrary circuit, I don't know, take some Fredkin gate or whatever. It's like given some arbitrary quantum circuit, you can turn every gate here into just a stochastic map or some kind of conditional probability table, but after doing that, you have to also introduce this expansion in between every gate, right? You have to compensate for this loss of information that necessarily is there when you just do stochastic things. Because by definition, almost stochastic means something random and noisy, right?
There's like some kind of like inference, what are those things called? Like gates, some kind of like inference gates, or like you need to inject what the observer is doing. If you assume the observer is doing the expansion, you need to inject that at every point and that's the thing that's creating the negative probabilities here. Would that make sense if you wanted to like explicitly put that in?
Yeah, well, I'm just thinking about it now. It's it doesn't matter what observer is doing, just a matter of fact that you have to compensate for your loss of information. So every negative probability that you see in the quantum world, in the quantum theory, can be, I think, explained by re-injecting this information back into the system, right? Because without it, everything looks stochastic. Or you can at least reformulate it using stochastic maps and all that. So it's probabilistic, but because physically you can't really have loss of information, you have to recompensate and re-expand all your probability vectors in the direction that they're really pointing. That's like the minimal inference that you can do, right?
But isn't that like making an observation is like making an inference?
Ask it again. I can't.
So isn't doing inference like making an observation? Every time you infer,
you can do inference kind of backwards and forwards in a way, right? Here, maybe I have to clarify that this inference corresponds to the backward inference. You have to figure out what was the cause of this.
Okay.
You know that the noise appeared, right? You know that there's some noise and the information leaked from the system, and you have to recompensate and do the backward inference to determine what was the state before that, right? But forward inference is pretty simple. You just again throw coins and just introduce more noise into the system, right?
But both of them would have the same effect as what you're showing here with this expansion introducing negative probabilities.
They're not having the same effect. They have the opposite effect.
Opposite effect, but the idea is that you can constrain where negative probabilities exist in inference, whether it's forward or backwards.
You can decouple
Mm.
negative probabilities completely and just only as expansions. Maybe that's what I was saying. It's like you can encounter arbitrary quasi-stochastic maps in quantum computation. Like if you just get an arbitrary gate, arbitrary quantum channel, it's going to correspond to some negative probability matrix, right? But you can decouple every negativity just as an expansion. So we can think of it as some stochastic thing plus expansion.
And is it always expansion, even though it's negative inference? You're still expanding.
Yeah, it's negative in a way that you have negative probability, but expanding in a sense that you expanding in the probability space. Your distance to the most uncertain state is grows, right? And most uncertain state is the center of the block sphere. That's the noise.
Interesting. Oh, that's a cool way of phrasing it. Okay. Okay.
Yeah.
So every time you infer, you're getting you're getting further away from the most uncertain point. That is basically what inference is.
Yes.
Like Bayesian inference, at least.
Yeah, it's like there's no stochastic way of representing rotation in probability space, because every stochastic map inevitably puts you closer to the center, right? Or to some point. It depends whether it's doubly stochastic, but that's details. To some point, it's like has some fixed point, and that's where any probability vector necessarily would go if you just apply this map many times, right? But in order to constrain yourself to a surface and maintain the information, right, to keep your states on
the quantum information,
the quantum information, or just this uncertainty representation of just a distance to the noise, right? It's like, or entropy. Entropy is not a good metric. It's like actually varies across the block sphere, the Shannon entropy, right?
Yeah.
But the von Neumann entropy is constant along the surface, and that's and also the distance is constant, right? And that's what this expansion is compensating for. So like you do some stochastic things by introducing noise, by going inside the ball, the sphere, but you have to re-expand, inject information to the system in order to compensate for that loss. And this process of and the combination of those processes is what quantum processes are.
Okay, so it's almost like the opposite of making an observation. Then it's actually like keeping yourself, avoiding observation, avoiding collapse to a purely stochastic process. You want to maintain the quantum state in some way. You have to almost like shield that state from observation. So every time you go through a logic gate, you like try to make some kind of inference, you have to shield it from some, and that like there's some kind of process that expands it back to the surface of the quantum state.
There's some kind of process. It's like more classically or conventionally, that's what I think people usually call collapse, right? Because what usually people describe as a collapse of the wave function, it's like you have a quantum state, you measure it, and it collapses to some other pure state, right? That is like parallel to the whatever observable you picked, right? Even though mathematically the projection produces a mixed state which is closer to the noise, right? It has larger entropy and less information. But the collapse of the process that makes this mixed state pure again, that's reinjection. Okay. In a way, that's the same as collapse, right? But now
but I thought collapse moves it away from quantum states. Because when you collapse, don't you collapse the quantum state? Isn't that what collapse is?
No. You're collapsing in a way you're just projecting it to some certain direction. So like if you have our random state here, like this is like it's pointing to this direction, right? But like picking, well, that's a bad state. It's very almost zero. Let's generate anyway. Right. Anyway, if you pick like the observable along the z-axis, this computational basis 0, 1, you project it literally to this axis, right? So like whatever projection is just going to point here. It's a very tiny arrow. It's almost noise, right? But when you say collapse, it's not just about having this mixed state where the projection happened. You also have to re-expand it back to the pure state, and that's what we call the post-measurement state. So like we measured it, but now the state is, we say that the qubit is still pure, but pointing in the direction along this axis, because we projected it on this axis and re-expanded it. So it's in a way it's equivalent thing is just formulated differently, not using some Hilbert space and quantum states and amplitudes, are just purely as a probability vectors.
Okay. So we don't have the exact information from the qubit, but it's collapsed to a point where it's like kind of like passed through a polarizer or something, and you've collapsed it to a different set of quantum probabilities, like a more definite set of quantum probabilities, something like that. Or I'm not using the right terms, but it's like
yeah, it's just like a completely different orientation, but without loss of information, right? It's still, it's like if it's a photon going through polarizer and it's going to some 45 degrees along that polarizer, it changes its polarization, but we not thinking about this state anymore, some kind of mixture with the device, with the polarizer. It's still a photon after you passes through. So in that process of passing through the polarizer, photon also purified itself because its quantum state got expanded back and the information actually not lost.
Yeah. So all the information of the photon is preserved, but somehow it's you've collapsed it to be in line with the polarizers.
That's what usually collapse means.
And you said then there's a post-measurement state. So is the polarizer in that example a measurement device? Or not necessarily? That's just because then what's the post-measurement is the expansion again back to the pure state.
Well, in a way we can put measurement device after the polarizer. And the fact that you have polarizer before that guarantees that you get your polarization along this axis because you rotated it. So I don't know. I don't know how even explain that where the actual collapse happens. That's the ancient problem. Is that I'm only telling about it in terms of probability theory now, right? And it's and also information theoretically, so that it just corresponds to this compensation of information that's been lost due to this discarding of the device, right? You have to re-expand it. So that's kind of neat that you can also diagrammatically represent this kind of process. And that's the basically what it boils to, that this process of inference that requires you re-injecting the information back into the system is what it's all the problems with things like hidden variables, because you can't really, as soon as you, that's another way of explaining why local hidden variables are impossible without like going into so deep as like Bell inequalities on that. You as soon as you it's like it's like my intuition now is that as soon as you have something represented by hidden variables, that's what we essentially was doing here, sampling a bunch of points along different orientations of our tutoring. Those can be thought of as some hidden variables, right? You can rearrange them, and then you can, and as soon as but then you would have to measure those, right? At least. So, and when the measurement happens in the process I just described with this discarding of the device, you have to somehow re-inject this information and do the inference, right? But how the inference can happen locally on the hidden variables isn't clear. It's like as soon as it's a single system, it's fine. You can think of it as a distribution. You can kind of sample it, determine what the distribution was before this noisy process, and you can resample from this expanded distribution. That's fine. But as soon as you have two qubits that are correlated, maybe it's two particles, entangled particles, going to Alice and Bob again. Familiar CH. As soon as there is a correlation to some other system, there is no way locally to do this inference process without destroying correlation classically.
Well, wouldn't it be something like, here's just like a crazy idea. So wouldn't it be like arbitrarily or randomly uniformly take 50% of these dots in this block here and then put them in like Alice's photon and then put the rest in Bob's photon? Then some of the information you could still make the same inference on both, because you just like, it's like you're just splitting it into two.
Well, that's what you don't have to split it. It's like, imagine that one way of to making correlated sample of points like that. You just Bell state is actually a special state that represents maximally correlated thing. It's like there's like both the particles go into Alice and Bob are completely random in some sense, but not completely random because we have this lower bound at uncertainty. It's like you have to keep in mind that there's some information, but it's like very minimal. It's a minimal of information.
Mhm.
So you sample. So you basically send these boxes to Alice and Bob. All those boxes are kind of look random to both Alice and Bob individually, but they are correlated.
Yeah.
And whenever Alice wants to measure their part, maybe it like does some local things that just rearrange them. That's fine, right? But as soon as it like tries to do some measurement, or maybe perform some other correlation with some other device, or with some other quantum particle, then the inference has to happen and rejection of information, and that can be explained with just with having this box of just hidden variables, because you have to manipulate the distribution itself.
Yeah.
But because the distribution itself just looks random, you have it. But then all the information in the correlation, there's no way to sample from this locally re-expanded distribution without like considering other part in any way. So that's what I know. It's hard to explain what's happening, but it's just
I mean, like I said, let me try to make like a very naive rephrasing of
Yeah.
that. Like, what if you just have, if these are all the hidden variables like in this box that you have here, and you just take like a handful of them and you put them in one entangled particle, and you take the other handful and put them in another entangled particle. Every time you expand, aren't you just sampling from those hidden variables? But because they have like similar distributions or whatever, that expansion is going to be the same in both.
well, the expansion is the same, but how you actually perform this expansion? You on the level of those samples.
Not just sampling from the hidden variables, the original hidden variables that were in the particles to begin with, when they were still the same particle, before they split off.
But well, we can think of this as the same particle, the whole entangled pair of particles as the same particle, maybe split parts.
Mhm.
But that's not the point. Is that okay? If there's a hidden variables that represent some distribution, and you know that if you measure it, you will lose the information. If you measure it classically by just discarding some stuff,
Mhm.
right? Because you can represent it as a stochastic process before this expansion. It's like everything up to this thing, this gray box, is classical, right? You can do it. You can like correlate it with the device and then discard it, but that's gonna lose the information.
Mhm.
So you can, in a way, you can classically sample from some a more uncertain distribution, but that's not the actual distribution that we observe. You have to inject this information back, but you can't inject it without destroying the correlation with Bob or something.
Yeah, I get that point. So is there any way to carry like some spare quantum stuff to re-inject along with it that kind of is preserved, almost like a battery or something, and then you can just expand from that, like that comes with the particle?
No, I don't know. That's how this mechanism can be explained in this mechanistic ways. That's the this is the big question. It's like that's why I've been previously talking about like how we can, after essentially when this reinjection has to happen, we have to send some message back to the origin of that correlation,
Yeah. Okay.
right? That's how you can, one way of explaining, and how this super deterministic property. But
Mhm.
on non-locality, you have to do something like backwards in time.
Okay, and that's non-local.
Yes.
Okay. Well, I would argue that maybe there's other ways of reframing that doesn't give you this terrible paradox, but the way it's currently, defined, it's non-local.
Mm-hmm. Yeah.
Wow. Yeah, that's a problem. Interesting. There were some comments here. Is this a specific collapse postulate? Means was comments in there as a
Oh,
question.
well, this is specific. Yeah, that's what we. Yeah, the specifics here is just we try to explain the collapse postulate in terms of probability distributions, and in terms of information transactions, informational
Okay.
transactions.
But it's really cool that you can split out this expansion thing as something specific to. It's a nice way of thinking about it in your head. You kind of like compartmentalizing the probability side of it, to maybe try to help figure out what's going on. Very cool.
Yeah, this gray box is the it's basically just
it's happening. Like it's definitely happening, but try to try to explain how it's happening locally is the issue. Like trying to figure out.
Yeah, it's like by itself is just like a box that, like as a diagrammatic things, you can just multiply vectors by each other. It's fine, right? But as soon as if you want to try to explain it locally, and with this kind of hidden variables, that's where it breaks down. But at least we isolated the problem to just a single gray box here.
That's cool. So we actually we opened up the black box, and inside the black box we found a little gray expansion box. So we've kind of
we reduced all the inferential retrodiction problems and negative probabilities to just one type of those, which are just expand your probability vectors and injecting information.
That's really cool.
Yeah,
it's like when you study computers and you really figure out what's happening at the hardware level. Normally you just have the CPU, but then when you actually look inside the CPU, you can figure out it's a combination of some other stuff, and then the mystery goes deeper and deeper until you really figure out what's going on. So it feels like we've gone one level deeper, at least for now.
I have some weird. I don't know what I can just scroll through it. I also have a separate notebook that just me trying to also go into that inference problem a little bit deeper. But just the same kind of expansion again, but also explained again in a smaller on a smaller example, but also in a different way, in different kind of ways. That's like you can think of this expansion as just as a Bayesian rule iteration, as just solving differential equations, or maybe you can think of it as an optimization problem of minimizing the likelihood. You can do this inhibitor problems that I had, which is like the closest you can get to the idea that actually having this hidden variables explicit, but you have to have this idea of retrying your original thing and and delaying it, right? You can even do it with a gradient descent, stochastic gradient descent, so that you can relate to this process of inference to the neural networks to some degree, right? And like some Monte Carlo Markov chain Monte Carlo sampling. Yeah. Now this is another picture for the expansion. It's like given this is like before expanded distribution, it has this form. Expansion, you can think of it as just on this bars of probabilities is basically if the probability higher than the average, it gets larger. If it's lower, it gets smaller. So it's in a way just stretching or spreading your probabilities away from the uniform one. This is just if it was a uniform distribution, it would be one half 50-50, right? Just two equal bars. But if it's not, you can expand it, right? So that's the process of expansion. And the square root of 3 is a particular expansion rate for the qubit. what's interesting here.
Okay, so there's some other ideas here that I wanted to mention. I was asking you briefly about thinking of the 4D version of a block sphere, and then that's basically a block ball, right? And then, or there's another way you can do it, maybe with colors or something like that.
Well, hold on. For 4D version of the block sphere, depends what you mean by that. So the block sphere for the qubit is 3D, is because essentially 2 squared minus 1, 2 is for the qubit, right?
Yeah.
If you
So
want to
it's
increase your Hilbert space dimension to 3, your block sphere would be 3 squared minus 1, which is 8.
And that's a tetrad, or what is it? No, it's not a qubit anymore. So something but tribid.
Qutrid, something like that. Qutrid.
Qutrid, okay.
Yeah. So
but there is a way to visualize it. There's
yeah, there's some ways I've looked a little bit into them.
But it's not necessary. It's just interesting to explore what the 4D case would look like. But yeah.
Well, actually, one more thing, I've been looking recently into this. I learned this thing that called Karpelevich theorem, which is essentially potentially can answer the problem about the shape of this quantum Hilbert spaces in higher dimensions. And this particular one, because this term comes from a theory of stochastic matrices. This is cool pictures. This is about the shape of eigenvalues for stochastic matrices. And they have there's some complicated theorem called Karpelevich theorem that says that the actual eigenvalues are constrained by this weird shape with arcs, right? And because this is how all the stochastic matrices are distributed there. This is how the unitary matrices distributed there. You can see kind of this lower bound of uncertainty already there. That's that's how this block sphere is hidden there, in a way, right? So in a way you can think, and because this map is always two-dimensional, it is a complex plane, right? This shape, in a way, can potentially shed some light on the shape of all the cuplexes in higher dimensions. Because I haven't found any reference together that mentions Hilbert spaces and Karpelevich theorem. But here I think there's the potential link for mathematicians to explore, right? Because this kind of
Really
arcing of there may relate to the fact that block spheres in higher dimensions have some kind of also some arcing inside, because you can there's a fact that generalized block vector, for example, for the qutrid, each qutrid pure state is on the surface of the hypersphere in a dimension, but not every point on the hypersphere surface is the pure state. So it's kind of, it has some arcing there, but in higher dimensions. So it's hard to visualize it, but because like this, maybe it's like doing something like this, but in higher dimension. I don't know. Just
while you've got that image up on the notebook behind it, can you scroll up to the point where you had the icosahedron? Icosahedron.
Icosahedron. This one. Not this one.
No, not that one. Actually, just go a bit up. That we had the two tetrahedrons overlapping.
Oh, okay.
Yeah. Is there a shape that matches the points on the left with the right? If you rotate.
Like this points, hold on, I just don't remember which shape. This is for yeah, this is for qubit, I think. This is already block ball. I should have done it for qutrid or something. I don't know. The fact that this looks circular, maybe if I've done it for qutrid, then there's some surface that would describe to some degree what's the shape of the qutrid in this 8-dimensional space. who knows?
Very cool. I put just to finish the geometric ideas, I put 2 links in here of the 4 polytope and then the 128 cell. But if you look at the Wikipedia articles, it's kind of interesting, and one of them looks similar to this thing you've just shown us now with this circle and the kind of the lines that go through it. So as we were saying, the 128 cell is the largest platonic solid at 4 dimensions, and you can actually click on show for regular convex 4 polytopes under geometry, and it will give you like more. If you scroll down to under the geometry section, you can click on show at the bottom.
Okay.
No, it was further up. It was the second. It was the second subsection, right at the top. Above
Okay.
this, yeah. So just above visualization, you see where it says regular convex 4 polytopes. You can just show those.
Yeah.
And then if you click on the 128 cell, the second link I shared, there's some stuff there which looks pretty interesting. So that cool picture was so interesting. I shared it on the Discord server, I think last week or the week before. Just randomly, I was like looking at these things. I was like, wow, that is such a mind-blowing thing, especially when it rotates and these things like intertwine with each other. It's like really cool stuff. I didn't realize it would would be like related to the topic this week, but it was kind of like a cool coincidence. So somewhere here, I'll find the exact link. There's a point where it actually has these couple of things. There. So if you go at the top of this 128 cell article, there, isn't that the Karpolov thing that's happening there on the right?
What? Where?
Go right to the top.
What?
Go to the top of the article. There. Just scroll down. So you'll see there's scroll a bit more down. You'll see there's this thing. Isn't that kind of like the Karpolov situation?
I don't know. What?
Because you had it in.
Far-fetched.
Okay.
No, this is just a projection. It's not a complex plane. Also, like, looks symmetric. This is like clearly.
If you scroll up on your one, there was that thing that you were showing on your notebook. There was that thing that you were showing where it like has those lines. Go back up. To the top, I think you had that thing. This thing.
Well, this one is. I think it's just a. This is just roots of unity. There's nothing. It's just points on a circle.
Okay. I don't know, my visual memory just like linked those 2 things together. Just associatively looked similar. So I wanted to ask about that.
Yeah. Who knows? So like this is the complicated formula from some papers about what's the actual arcs, the shape of arcs. And if also this formula, if somehow it relates to Qplex, it would be interesting. But that's just a crazy hypothesis.
Interesting.
Um,
Okay, cool.
Yeah, so I was also wondering about the point groups in 4 space, because there might be bigger ones than 600. I thought I remember something about 720 size point groups, but I think there might be a 14,400. There's an article about it here.
Maybe it depends what you count.
Mm-hmm.
Like in this 600 cell, there are 120 vertices, but 720 edges.
Right.
Memes are saying, is it the 14,400 co-exit group or something? What is the wild group? Wild group.
File group. Like given like a
I
set
know
of
why.
root vectors, like a root system, symmetries that respects them.
But it's related. Is a wild group different to the vowel something in when we talk about quantum stuff? There's also
No,
some.
not this one, I think.
Okay.
There's other wild stuff in quantum.
Mm.
Like there's a wild. We even have a wild transform, right? You have quantum wild transform, which is essentially what allows you to go back from all those phase-space transformations. Well, that's what at least that's what we call it, right? It's like opposite. Go from probability space or phase space to Hilbert space. It's a backwards map from probability to Hilbert. There's
Okay.
also one Heisenberg group.
Heisenberg. Okay. These things. Okay. Cool. That was quite interesting. So what are you kind of like your next steps to give us a hint of what you're currently working on? You're talking about examining these different ways of thinking about the inference, right? Is that where you're currently working?
It's yeah, try to figure out like this more computational realizations of that process of inference. How you can explain it by retrying your probability distributions so that you can do inference, but non-locally on a hidden variables, but in a more operational form, right? Just applying stuff to your ensembles in some weird ways, but at least that can be simulated.
Okay, cool. Thanks for that. Yeah, so just a couple of things to mention. So as we close up the stream, is there anything else you want to talk about right now, or can we mention some things?
No, let's mention some things.
Yeah, and then if you can save this notebook as well, that'll be great. We'll add it to the description.
I'm gonna say
Yeah.
I'll do this. It's kind of too many nodes. At least this
one. All right, cool. So yeah, just a couple things to mention. Then there's the NKS Book Club again, which you guys should be aware of at the moment on Discord server every Sunday. We also have the Wolfram Winter School that will be starting 6th of January. So be sure to sign up on that. It's going to be more physics focused specifically. So with physics projects and similar type of research. So if that's your forte, just please apply, and then we can see if we can get you in. And then that's the main things that we want to cover. There was something else, but yeah, I don't know. Well, if I can remember what I was gonna do all the notifications, I think I'll just post it on the Discord server. And if anyone's in San Francisco this weekend, there is a hackathon that's going to be taking place with Physics Cross AI that we can share some information about, or you can just ping me also on Discord, where we can give you information on that if you guys have some interesting things you want to work on over a single weekend. That might be something we can arrange for you. It's a collaboration with Wolfram Institute there. And yeah, that's it for now. So thanks, Nick, for sharing. Oh, this is what I wanted to say. Tomorrow we have a live stream with Gabriel Carcassi. So this is like going to be a very cool seminar. We're going to explore some interesting things. Maybe Nick, can you talk a little bit about Gabriel's work and what kind of stuff to expect from that live stream? Like what kind of field of science does he talk about?
Well, Gabriel has this cool project called Assumptions of Physics, and he has this notion of reverse physics. Well, he's going to talk about more about it tomorrow. But it's about like coming up with the minimal assumptions, like an axioms for all the physical things that you observe, right? And right, in the minimal manner, and it's like all about how things like an entropy, like Hamiltonian evolution, like essentially the things that we talk about, but for more axiomatic approaches, more classical things like what is the actual minimal theorems and axiom we have to impose in order to derive everything.
Interesting.
And we're gonna ask about him tomorrow, help all about his ideas about quantum and something like a non-additive quantum measure and things like that. That's
Very
what I'm
cool.
looking forward to.
Okay, great. Yeah, hopefully all the researchers can be online for that one. I'm gonna be on a flight, so I won't be able to make it, unfortunately. But yeah, hopefully we can bring him back for more live streams in the future as well. So this is that's exciting one. So everyone stay tuned for that 2 p.m. Eastern time tomorrow. Great. Okay, thanks everyone. We'll catch you in the next one.
Awesome. Thank you.
Cool.
Everyone.